Hi everybody. For the next little while we're going to talk about areas of sectors and segments of circles, also some arc lengths, and it's a pretty interesting little workout. I'm going to start with this picture. We got circle X, that looks like circle C. I'm going to make it be circle X with radius 12, and this angle is a 90-degree angle right there. Yeah. Okay, give the length of arc AB. Couple things I got to remember about arc length. First, the circumference of a circle is given by 2 pi r. We're going to always need that formula. So what would be the circumference of this circle? Since its radius is 12, it'd be 2 times pi times 12. That'd be 24 pi. Now that I know the distance all the way around the circle, I can figure what part would this length have to be. And I'm convinced that it would be 90 3/60ths of the full circumference, and the full circumference being 24 pi. And you recognize that 90 3/60ths is the same as 1/4. So 1/4 of 24 pi. And that would be 6 pi. So we're talking about 6 pi, and that would be millimeters since that was in millimeters, but I'm just going to keep it at 6 pi for right now. Then I got to come up with the area of the sector. Really a similar idea. But instead of arc length, we're going to start off with the area of the full circle. And a formula that you'll need to know for the rest of your life is the area of a circle is given by pi times the radius squared. So let's find the area of this whole circle. Its radius was 12. Pi times 12 squared would be 144 pi. So now I know the area of the full circle. So what part would be in the sector? And what you must know is a sector is bounded by a radius, and an arc. So this whole segment, this whole sector right there is what we're talking about. I can find that sector. It will be 90 3/60ths of the full area of the circle, which was 144 pi. And you recognize again this will be 1/4 of 144 pi. And that'll be 36 pi units squared. That'll be the area of the sector. Now, we're going to start to get interesting. In a little while, we're going to find the area of this little zone that is shaded. That's called a segment of the circle. But first, we'll need the area of the triangle. And that'll be really simple because its base is 12 and its height is 12 because it's a right triangle and it's described in a circle. We can get the area of that triangle quickly and easily. It'll be 1/2 times its base, 12, times its height, 12. And that'll just be 6 times 12, and that's 72 units squared for the area of the triangle. So give the area of the segment, that shaded zone right there. What must that be? What I hope that you're thinking is the area of the segment. Let me write a couple things here. The area of the segment is equal to the area of the sector minus the area of the triangle. Everything inside of this zone, take away the triangle, would give me the segment that I care about, that shaded zone. So the area of the segment, let me work that out with you, ought to be, hey, what was the area of that sector anyway? 36 pi minus, hey, what was the area of that triangle anyway? 72. So there we have it. The area of the segment is 36 pi minus 72. Somebody might want a decimal for that, but I'm happy with leaving the answer just that way. So let's check this next guy. Circle P has a diameter of 18. I always go right to the radius right away. Radius would have been 9. And I'm going to be thinking about the circumference in the area right away. Here it asks about the arc length, so let's figure out the circumference first, and then we'll figure out what part of the circumference this arc length is. With a radius of 9, the circumference of the circle is given by 2 times pi times the radius of 9. So our circumference is 18 pi. So we got to ask ourselves, what part of the circumference is this one? And I'm thinking it's going to be 120, that's the central angle, over 360, that part of the full circumference of 18 pi. And you recognize, I expect, that 123/6 is really 1/3. That's 1/3 of the distance around that circle, which was 18 pi. So that would have to have been 6 pi for the length of that arc. Give the area of the segment. Now that segment, you know what, here it says segment, here it says segment. This must have meant sector. Let's make that correction right there. After all, a sector is bounded by the radius, and the arc. We would want to find that sector before we found that segment. Let's find out about that sector. Same idea, but I would want to know the area of the whole circle first. Since its radius was 9, the area is pi times the radius squared, 81 pi. But what part would this sector be bounded by the radius, and this arc? I think it's going to be 1/3 of the full area truly. I'm going to think it's 123/60ths of that full 81 pi, which is in fact 1/3 of 81 pi. And 1/3 of 81 is 27 pi. So that would be the area of our sector. Hey, what's the area of that triangle? Well, I'm going to sketch the triangle again. You don't really have to. You could work it right from that picture, but I just want to be really clear. And I know that this is a 120-degree angle, and the radius was 9, so this distance is 9, and that distance is 9. I got to get a base, and that's a pretty good-looking base, but I need a height for it as well. And to get that height, I have to extend that side and go to it perpendicularly. And this is the altitude I should use to find the area of that triangle. And since that was 120, this angle would have been 60. I think the short side right there would have been half the hypotenuse, 9/2. And the longer leg, which is our altitude this time, is the short side times the square root of 3. 9 square roots of 3/2. Now, how can you get the area of the triangle? And I say, yes, I could. Area of that triangle is going to be 1/2 times its base, and its base was 9. Yeah, that was that base right there. That's 9, and we got that altitude right there. So this triangle could have fit here, I think. Times its base of 9 times its height of 9 square roots of 3/2. And if you would multiply with those things straight across the top, it looks like we'll get 81 square roots of 3 over 2 times 1 times 2 over 4. 81 square roots of 3/4. That's the area of the triangle. Now what about the area of that segment? And you bearing in mind that the segment is this zone I'm shading right now. It's inside the sector, but it's outside the triangle. And it is every time going to be the area of the sector minus the area of the triangle. That's how you get the area of the segment. The area of the sector was 27 pi minus the area of the triangle, which was 81 square roots of 3/4. That's an ugly one, but 81 square roots of 3/4. And I'd say that's the area of the segment right there. If somebody wanted a decimal on it, we can work on that, but I don't care for it. I'm happy to have what we have. Let's play again. This angle is 135 degrees. And the radius of this circle is 12. Going to get the length of that arc BC, and probably going to work it just like we did before. Hey, what's the circumference of the whole circle? What's the distance all the way around it in the first place? Since it has a radius of 12. 2 times pi times 12, 24 pi. What part is this arc length of that full circumference? And this will be 135, always the central angle, over 360 times that full circumference of 24 pi. So you can we reduce that 135 3/60ths? And I say, yeah, you can, because 45 goes into both of them. That's the same as 3/8. 45 goes into 135 3 times, 45 goes into 360 8 times, so it's 3/8 of 24 pi. And this is working out kind of cleanly, isn't it? You can multiply that in lots of ways, but if you went 8 into 24, this is going to give me 3, and 3 times 3 is going to give me 9 pi. Yeah, you could have gone 3 times 24, 72 pi divided by 8, still going to be 9 pi. That's the length of this arc. Give the area of the sector. Well, first I'd want to know the area of the whole circle. Given by pi times the radius squared, there's 144 pi. But what is the area of the sector bounded by this radius, and that arc? It will have to be, probably going to be 3/8 of it, isn't it? It's going to be 135 3/60ths of the full circumference, which is 144 pi. Excuse me, the whole area. And that becomes 3/8 of 144 pi. And you can hit that with a calculator, I figure, but let's leave pi for later. But I think 8 goes into 144 18 times. And 18 times 3 is going to be 54. So I'm coming up with 54 pi for the area of the sector. What's the area of that triangle? Well, it's got a 135-degree angle. I'm going to sketch it again. Don't really have to, but I think it's a pretty good idea. It is isosceles. This is 12 and this is 12. And with that 135-degree angle, we're going to have to get an altitude, and I would drop this altitude right there to the line of the base perpendicularly, because this angle was 135 degrees. It leaves a 45-degree angle right there, doesn't it? So we got us a 45, 45, 90 to work with right there. I care about the length of the altitude to go from the hypotenuse to the congruent sides, and a 45, 45, 90, I got to divide by the square root of 2, and 12 divided by the square root of 2 is 6 square roots of 2. That's what our altitude would be. Now, can you give me the area of the triangle? I figure I could, huh? 1/2 times its base, 12, times its height, 6 square roots of 2. Clean that up a little bit. 1/2 of 12 is going to give me 6 times this other 6. I got 36 square roots of 2. Unit squared. All these areas should be unit squared. We should be careful about that. What about the area of the segment? And now you must remember, the segment is the shaded zone right there. It's inside the sector, so it's inside of that 54 pi, but it's outside of that triangle, so it does not include that 36 square roots of 2. It will always be, for the area of the segment, the area of the sector minus the area of the triangle equals the area of the segment. Area of the sector, yep, 54 pi. Minus the area of the triangle, 36 square roots of 2. Square units, that's the area of that segment right there. I've drawn a couple other things I want to show you, though. Let me show you about these ideas. I think they're really interesting little ideas. Work with circles together. And let's say that this triangle ABC, has semicircles on it. And ABC is a 6, 8, 10 triangle. I think I'll let this side be 6, this would be 8, and the hypotenuse there, opposite the right angle, it was 10. Give the area of the shaded zone. And what we have here is 3 semicircles. I think you'll find it interesting. What's the area of that semicircle right there? Because this is a 6, 8, 10 triangle, this side is 6, this radius of that semicircle would be 3. The area of that circle would be pi times 3 squared, and that'd be 9 pi. But I think the area of that semicircle is going to be half that much. So it's 9 pi over 2. That's what I get for that little zone right there. And because this is a 6, 8, 10 triangle, this side is 8. But I need the radius of that semicircle, and that would have been 4. I'll think, what's the area of the full circle with a radius of 4? Pi times 4 squared. That'd be 16 pi. But this is just half of that circle, isn't it? Half of 16 pi, that's going to have to be 8 pi. Now what about this semicircle up here? Well, because this is a 6, 8, 10 triangle, that hypotenuse is 10, and the radius of that semicircle would be 5. And I would find what's the area of that whole circle first, and that would be pi times 5 squared. That's 25 pi. But we only got half of a circle, don't we? Because that's a semicircle, and that would have to be 12 and 1/2 pi. 1/2 of 25 pi. And here's something I know to be true that is very interesting. The area of this semicircle plus the area of this semicircle will always equal the area of the larger semicircle. You check on that. 9 pi over 2 plus 8 pi over 1. Is that equal to 12 and 1/2 pi? Yeah, this is really 4 and 1/2 pi, isn't it? Plus 8 pi. That's going to give you 12 and 1/2 pi. Turns out you could put equilateral triangles on each of those on each of those legs and the hypotenuse, and they would also add up the same way. Put squares on them, they still will. Any similar figures there add up in that interesting way. Let's play with a couple more. I won't talk too much longer. Square ABCD has perimeter 24. As soon as they tell me that, I go around thinking how big the sides are. If the perimeter is 24, each side would have been 6. Give the shaded zones area. We think about that. Just a general statement. The area of the shade. What should it be? And what's clear to me is it must be the area of the square minus the area of the enclosed circle. I want everything inside the square, so it has to be in that area, but outside that circle. So we're going to subtract that away. So let's get the area that is shaded here. The area of the square, well, it's a 6 by 6 square, that ought to be 36, huh? Minus, now what about the area of that circle? We'll need to know its radius. I believe that the diameter, the distance all the way across there is 6. The diameter of the circle would be 6, so the radius is 3. So what's the area of that circle? 9 pi, huh? And I would report to you, yeah, the area of those zones all add up to 36 minus 9 pi. Now, if somebody asked me, hey, what about this area right there? Just that little piece and that little part right there that I'm shading kind of darkly. I think I can figure that amount too. I think it's 1/4 of this amount, isn't it? So I'd have to report that as 36 minus 9 pi over 4. Just that little shaded area right there. I've got one more I want to show you, please. Same kind of idea, but this time, instead of having a circle within the square, we've got a circle surrounding the square. The square is inscribed in a circle. The square ABCD is inside of circle X. If the circumference is 12 pi, give the shaded area. And I hope you're thinking, well, if the circumference is 12 pi, and the circumference is also 2 pi r, we ought to be able to figure out the radius, huh? If 12 pi is 2 pi r, the radius has to be 6. If we would like to get the area of this shaded zone, think of it with me ahead of time. Mustn't it be the area of the circle minus the area of the square? That would equal the area that is shaded. And I don't think that's a dumb thing to write there that ahead of time. Then we're just going to figure out, hey, what's the area of that circle? What's the area of that square? We'll have that figured out. I want it to be inside the circle, but outside the square. That's that shaded zone. With a radius of 6, hey, I can get the area, let me show that distance right there. Yeah, with that radius of 6, we got to find the side of that square in a minute too. I think we'll be able to do that. I think there's a right angle right there. So with a radius of 6, the area of the circle is 36 pi. Minus, now what's the area of that square? If this is 6 and this is 6, wouldn't the side of the square have to be 6 times the square root of 2? I'm sure that that's a 45, 45, 90. So now I know the side of the square. Hey, what would be the area of that square? It'd be 6 square roots of 2 times 6 square roots of 2. Easy to make a mistake there, but that would be 36 square roots of 4. That's 72, isn't it? So back to this. Hey, what's the area of that shaded zone? 36 pi minus the area of the square, which was 72. That's what that area has to have been. Now, if somebody jumps out of a taxi cab and says, hey, all I want is this area right there, this little piece right there, which would be a segment of a circle. There's lots of ways we could work it out, but I bet you right now you could agree with me that this is one of 4 equal parts. So that little zone right there, if we cared about it, would be 36 pi minus 72 divided by 4. I know what you're thinking. Yeah, we can reduce that fraction, can't we? 36 pi over 4 would be 9 pi. Minus 72 over 4. Hey Alexa, what's 72 divided by 4? I think that's about 18, isn't it? About 9 pi minus 18. That's what we're talking about for the area of that little shaded zone right there. Now, I've got a little workout for you to do, and it involves areas of segments and sectors and such, and give it a good shot and get it to me. Thank you very much. I appreciate your time.